All right, so what we are going to talk about today is transient analysis of series RLC circuits, because I'm going to probably falsely assume that you all watched the video that I told you to for Monday. So let's say that we have the following circuit. I'm going to put a resistor right here, R. I'm going to put an inductor here, L. Capacitor here, C. And connected to this series combination of resistor, capacitor, and inductor, I am going to have, let's say, a voltage source, Vs. And here I'm going to have a switch. And our switch is closed until it opens at t is equal to 0. I'm going to define the voltage drop over my resistor to have this polarity, the voltage drop over my inductor to have this polarity, and the voltage drop over my capacitor to have this polarity. And I am also going to keep track of this current I of t. And after the switch opens up, I of t is flowing into the positive polarity terminal of all of my elements, which is why I chose that particular polarity. Please note that while the current I of t is common to all of these elements, R, L, and C, it is representative of the inductor current, which means that it cannot change abruptly, right? So whatever value it had at t is equal to 0 minus, it must continue to have at t is equal to 0 plus. So by inspection, we can see that for time less than t is equal to 0, so while that switch is closed, our resistor will have a voltage drop over it that is negative Vs based on the polarity of the terminals given here. And our capacitor will have a voltage drop over it, Vc, that is exactly equal to Vs, which means that our capacitor has some amount of stored energy, right? Because the energy stored by a capacitor is 1/2 CV squared. If V is non-zero, then there is energy stored in the capacitor. When our switch opens, what's going to happen is that the energy that's stored by the capacitor, some portion of it will be passed to the inductor, some portion of it will be passed to the resistor, and over time, we will find that all the stored energy by the capacitor will be converted into heat by the resistor, leaving us with a total stored energy of 0. All right. So during the transient condition, if I apply Kirchhoff's voltage law, what I'll find is that VR of t plus VL of t plus VC of t must be equal to 0. I can express all three of these voltage drops in terms of my common current I of t, right? So the voltage drop over my resistor is R times I of t. The voltage drop over my inductor is, hold on, LDI, yeah. L di by dt, and the voltage drop over my capacitor is 1 over C integral from 0 to some later point in time of I of x dx, where x is just a dummy variable for time here, plus Vc at 0. And all of this is equal to 0. So this is simply just a restructuring of my Kirchhoff's voltage law equation to put everything in terms of that common current I. And this leaves me with what's called an integro differential equation, which is kind of a pain in the butt to solve. So what we're going to do now to make this integro differential equation simply a differential equation is we are going to take the derivative of both sides. Okay, we're going to take the derivative with respect to time, which is going to leave us with R times the derivative of current with respect to time plus L times the second derivative of current with respect to time plus 1 over C times our current, because the derivative of the integral is just the function itself. And then when we take the derivative of this Vc at 0 term, that's the derivative of a constant, so it goes away. And lastly, what I'm going to do here is I'm just going to rearrange things very slightly. I'm going to divide both sides by L and rearrange. And so that's going to give me the second derivative of current with respect to time plus R over L times the first derivative of current with respect to time plus 1 over LC times our current function is equal to 0. This is what's known as a second order homogeneous differential equation. Okay, so for those of you who have had Math 245, you already know what the answer to this equation is, or at least what its form is. For those of you who have not yet had Math 245, what we are looking for here is a function where the second derivative plus some coefficient times the first derivative plus some different coefficient times the 0th derivative, or the function itself, is equal to 0, which is satisfied only by an exponential function, right? Because an exponential function, the first derivative is effectively the same thing as the function itself. The second derivative is effectively the same thing as the function itself. So what we are going to do is we are going to, I'm going to call it a guess, but it's not really a guess, that our current I of t is of the form A e to the st amperes. Okay? This is the exact same guess we made when we looked at RL circuits back in circuits 1, and it's valid for the exact same reasons. So if we substitute this relationship in, what we're going to have, so what's the second derivative of that current? So that'd be the first derivative. S squared is the second derivative, right? So if we substitute this guess value into our KVL equation, what we find is that we have S squared AE to the ST plus R over L times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And what I'm going to do now is I'm going to just group like terms. So we'll have A multiplied by S squared plus R over L times S plus 1 over LC times E to the ST is equal to 0, where this bit right here is our characteristic equation for our system. So our goal is to make this expression, the left-hand side, equal to 0. Well, there are a couple of different ways that we can do that. One is that if A is equal to 0, then everything on the left-hand side is 0. That's what I'm going to call a trivial solution because it effectively represents the system if it has no energy stored at the beginning, right? So everything was turned off. E to the ST can look like 0 if S is a negative number and we wait a very long time. But we can figure out what specific values of S will make this expression 0 by looking at this characteristic equation, right? So it's a simple second order or quadratic polynomial. So I would argue that we can use good old 8th grade math in order to figure out what the solutions are, okay? So using the quadratic equation, we're obviously going to have two solutions since this is a second order polynomial. We're going to have negative b, where b here is the coefficient of the s term. So that's negative r over l, plus or minus the square root of b squared minus 4a, which is the coefficient of the s squared term, which is just 1, times c, which is a coefficient of the constant term, so that's just 1 over LC. All divided by 2a. That's literally just straight from our quadratic equation that we all learned in, I don't know, high school, middle school, whatever. What I'm going to do now is I'm going to move this factor of 2 from the denominator into the numerator simply to make this expression a little less ugly looking, okay? So that's going to be negative r over 2l plus or minus the square root of r over 2l squared minus the square root of 1 over LC squared. So when I move this 2 from the numerator or the denominator inside the square root, it's going to look like a factor of 1/4, which cancels out the 4. And I am taking the square root of the 1 over LC term squared so that I have something squared minus something else squared. And we're going to give these somethings a name. So we're going to call this term alpha, where alpha represents the Neper frequency of the system. And it tells us how our system exponentially decays. It's very similar in concept to the time constants that we dealt with in circuits 1. Okay. It has units of nepers, which is a dimensionless quantity, per second. So alpha for this series RLC circuit is R over 2L. And we're going to call this term omega naught, where omega naught is our resonant frequency. No, just the square root of 1 over LC. Having units of radians per second, I'll write it down here. Omega naught is the square root of 1 over LC. Okay. The resonant frequency actually has multiple different definitions depending on what branch of engineering you're looking at. And in electrical engineering, it has different definitions depending on what application you're using. They are all actually representative of literally the exact same thing. It's just looking at it from different perspectives. Okay? So what the resonant frequency represents here is when the impedance of the circuit will be purely resistive, okay? Or when all of the capacitive reactance cancels out all of the inductive reactance. All right. For a mechanical system, it represents the frequency at which oscillations effectively build on each other. How many of you have heard of the Tacoma Narrows Bridge disaster? I see a couple of people nodding their heads. Yeah, so that's when some wind turbulence caused a bridge to start experiencing oscillations. And the oscillations that it was experiencing were at the resonant frequency of the bridge, so that effectively a positive feedback loop occurred, which caused the bridge to literally shake itself apart. Okay. So it tells us something about the point of mechanical failure due to oscillations. Well, in an electrical system, it's effectively where we're going to see ringing or resonance occur. Okay, and we'll see that specifically in a little bit. All right, so using the quantity alpha and omega naught, we can then express S1 as negative alpha plus the square root of alpha squared minus omega naught squared, and S2 as negative alpha minus the square root of alpha squared minus omega naught squared. Okay. S1 and S2 are what are values for the systems, or the natural frequencies of the systems. So these tell us how it behaves when there is no excitation, or when we're taking an excitation function away from our system, okay? Which is exactly what we're doing when we open the switch up and disconnect our voltage source. So, this leads us to our response, okay? So if we look at our guess value here.
So that would indicate that the frequency is too fast for those components, the inductor and the capacitor, to keep up, basically, with the oscillation.
I don't necessarily agree with that.
I hate to sidetrack a second.
Yeah, it's related to what's called the quality factor of a circuit, where the quality factor tells you effectively a relationship for energy conversion in the circuit, meaning how much I push the circuit causes a change in the output. It's a whole other bag of cats for a whole different thing. Yeah. All right, so if we look back at our guess value, we can see that our guess was AE to the ST. Well, we figured out what S is. There's actually two of them. A is going to be related to the initial conditions on the circuit. And due to superposition, we're going to have two distinct solutions. And the sum of those solutions is a solution in and of itself. So what I mean by that is, generally speaking, our response, y of t, is going to be of the form a1e to the s1t plus a2e. Okay. So this is a guess value corresponding to each of our two different values of s, where a1 and a2 are coefficients that are multiplying our exponential function and are related to the initial conditions on our system. So the voltage drop across the capacitor and the current flowing through the inductor, okay? This is our general solution, but there are sometimes problems with it, okay? So this is our solution specifically when alpha is greater than omega naught, okay? We call this type of system an overdamped system. In an overdamped system, that means it takes a long time for our response to settle to its final value, okay? So it means it's just going to take a long time for the voltage to decay to zero or for our current to decay to zero in this particular electrical circuit, all right? Now, I'm going to scroll up here because I want us to look at S1 and S2, okay? So when alpha is greater than omega naught, the guy under the radical here is a positive quantity, which means we have negative alpha plus the square root of something positive. It's literally just going to be a real number. S2 is also just going to be a real number. What if alpha were equal to omega naught? S1 and S2 would be equal to alpha, but that leads us to another problem, in as much as we have two initial conditions to satisfy with only a single S value, okay? So when alpha is equal to omega naught, we have to modify our response equation to incorporate a second initial condition. And so we are going to have y of t be of the form a1 t e to the alpha t, excuse me, to the negative alpha t plus a2 e to the negative alpha t. When alpha is equal to omega naught, we call this system a critically damped system. Now let's look at S1 and S2 again. for our final case. What if omega naught were greater than alpha? Exactly right. S1 and S2 are imaginary numbers, but they're complex conjugates of each other because the bit under the root sign is going to be the same, right? So we're going to have negative alpha plus blah, 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 and then negative alpha minus that same blah, 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 right? So S1 and S2 are going to be complex conjugates of each other. So alpha less than omega naught. And our response equation can be expressed as B1 cosine omega dt plus B2 sine omega dt. This expression multiplied by e to the minus alpha t, where omega d is simply the square root of omega naught squared minus alpha squared. We could get here deriving it using Euler's identity, but it takes time. This is an example of an underdamped system. In an underdamped system, we have what's called ringing, right? So the sum of two sinusoids having the same angular frequency omega d are going to look like a single sinusoidal function. We proved that to death in circuits 1. That single sinusoidal function is being multiplied by an exponentially decaying function. And so we're going to see something that looks like this. All right. So here's t, here's y as a function of t, and for a underdamped system, we should expect to see some sort of ringing like this, where I've drawn this kind of poorly, but it'll be okay. Effectively, what's going on here, actually, let me scooch that part down, is we have an envelope characterizing the exponential decay, and that exponential decay is multiplied by that sinusoid there. So we have oscillation that gradually settles to a finite value. So our red curve here is for an underdamped system. Our green curve, which I'm about to draw, will be for an overdamped system. And effectively, it's just going to be this guy. It's an exponential decay that takes a long time to get to its final value. And then finally, a blue curve will be representative of a critically damped system. And that's just going to be an exponential decay gets to its final value in the smallest amount of time without having ringing or overshoot. So these are our three types of responses that we should be able to observe in any series RLC circuit. Okay. Bear with me just a moment while I open up a table. For those of you that are physically here, it's the one I handed to you. Oh, good God, what did I just do? Oh, so that's the right one. There we go. How do I make this smaller? All right. So this is a table that I've created. Like I said a moment ago, for all of you that are physically here, you were handed a copy of it. For all of you that are on Zoom, here you go. I'll also post it on Moodle after today's class. This will also be the equation sheet that you have for exam 2. This is literally it. Okay. Excuse me. What this table summarizes is the response for all parallel and series RLC circuits, including when we have forcing functions included. So when we're not taking sources away, we're adding sources in. We're going to effectively just spend the next couple of days working example problems to illustrate things. Okay? Now I want to point out what I have included here. Okay. The response type is overdamped when alpha is greater than omega naught, which we discussed earlier. Alpha is R over 2L, which we derived earlier for a series RLC circuit. Alpha is 1 over 2RC, which for those of you, which I strongly don't feel is actually any of you, maybe Skylar, she's a good student. She got through half of it. Thank you for humoring me, Skylar. Alpha for a parallel RLC circuit is derived to be 1 over 2RC. Omega naught in both cases is 1 over root LC. I give you the response equation. Then I give you the derivative of this response equation. We're going to talk about how that comes into play in a little bit. Okay. So the goal here is that you should be able to use the table and never have to do any of the derivatives or anything like that yourself. All right. I give you a similar amount of information for critically damped parallel and series RLC circuits and underdamped parallel and series RLC circuits. So these are the equations that you are going to be utilizing when you're analyzing practically any and all of these circuits. The only other things that are going to come into play is that you're expected to know that the voltage drop across an inductor is L di by dt, and the current flowing through a capacitor is C dV by dt. All right, so what we're going to do now is we're going to work an example, excuse me, where we're going to put this table information into use. So I just grabbed one of my many circuit analysis textbooks. And the problem that we are going to analyze is this guy. All right. So we have a 12-volt source connected to a 2-ohm resistor connected to a 6-ohm resistor. Here we're going to have a switch, and our switch is going to open as T is equal to 0. Here we have a 2-amp source. Here we have a 4 ohm resistor, a 2 Henry inductor, a 2 ohm resistor, and a 1 farad or astronomically large capacitor, which I'm sure the author of this textbook chose purely to make the numbers pretty. All right. I'm going to label a couple of quantities here. So I'm going to call this VL of T. And I'm going to call this DC of T. And I'm going to call this current I of T. All right. Let's pick 2 of these 3 quantities. Which ones do we want to solve for? VC of T and VL of T. Okay, I'm going to veto VL of T. Oh, I, okay. So VC of T and I of T. Okay. The reason I was going to veto that, we can absolutely do it. It's just going to take longer than we have to do that. Okay. So I'm just going to put a green check mark by this guy and this guy. Okay. Those are the 2 quantities that we're interested in. I'm going to walk you through our approach. There are 2 homework assignments that have been posted, one on series RLC circuit and one on parallel RLC circuit. They're on Moodle right now. That is literally what we're about to do is literally the steps that I ask you to solve the problems in, so that there is no confusion or anything like that, okay? Our first step is going to be to determine whether the circuit is an overdamped circuit, a critically damped circuit, or an underdamped circuit. And to facilitate that, what we're going to do is we are going to look at a dead network representation of our circuit during the transient condition. Okay? So during the transient condition here means after this switch has opened up. Okay? So a dead network representation would look like this. Our 12 volt source, sorry, I should be using a black marker, is a short circuit. Then we have our 2 ohm resistor. Here's our 6 ohm resistor. We have the open circuit of our switch. We also have the open circuit of our current source. Then we have our 4 ohm resistor. Our 2 Henry inductor. Our 2 ohm resistor. And our 1 farad capacitor. So this, do we all agree that this is what our circuit looks like as a dead network, meaning our independent sources have been turned off during the transient condition, meaning after our switch has opened? Are we okay with this representation? All right. So the first question that we need to ask ourselves is, Is this a series RLC circuit or is it a parallel RLC circuit? Series. Okay. So the 2 Henry inductor is in series with the 2 ohm resistor, is in series with the 1 farad capacitor. This 4 ohm resistor up here isn't included because it's open circuited, and so it can't actually contribute to our response. Okay. So the crux of our analysis is going to be around the behavior of this 2 Henry inductor in series with a 2 ohm resistor in series with a 1 farad capacitor. All right. So I believe we are all in accord that this is a series RLC circuit. Okay. So because it's a series RLC circuit, according to the table I gave you and the derivation that I made you suffer through at the beginning of class, alpha is R over 2L, where R in this case is going to be the 2 ohm resistance. And then we have twice 2 Henrys, which looks like 2 over 4 or 1/2 Nepper per second. Okay, so the units.
I figured it out.
Yeah, okay, because a Henry is an ohm second. All right, now let's figure out omega naught. So that's going to be the square root of L times C, or 1 over L times C. That's the square root of 1/2. Units of radians per second. So which one's bigger?
It's the square root of that whole fraction and not just the square root of the bottom.
Square root of the whole fraction is the same as the square root of the bottom portion because the numerator is 1. Yeah.
Just make, okay. Thank you.
Is it? I asked that sincerely because I don't know what the square root of 1/2 is off the top of my head.
Well, would 1/2 be?
Let's find out.
If you rationalize the square root of 2, so I think it is slightly larger.
Yeah, so square root of 1/2 is square root of 2 over 2 or 0.707 blah, blah, blah. Yep. So alpha is less than omega naught, implying that this circuit is underdamped. Are we okay to this point? All right. What we're going to do next, analyze the circuit at t is equal to 0 minus to get our initial conditions, analyze the circuit at t is equal to 0 plus, see how it behaves then, and then analyze the circuit at t is equal to infinity so that we have all of the information we need to plug into that table now that we know what our response equation should be. So at t is equal to 0 minus, this represents a DC steady state condition, which means that we are going to replace all of our capacitors with their DC steady state equivalent. What's the DC steady state equivalent of a capacitor? Open circuit. We're going to replace our inductors with their DC steady state equivalent, which is a short circuit. All right. And our switch will be closed because we are at a point in time before our switch has opened. So that means that our circuit looks like this guy. And here is VC of 0 minus. And here is I of 0 minus. All right. So how do we feel like we should go about solving for these quantities? Source transformation, okay, on the 12 and the 2. All right, so the suggestion is to do a source transformation on the 12 and the 2. I tend to agree with that because what that's going to do is it's going to put a 6 amp source in parallel with the 2 amp source. They're going to combine together to look like 8. It's going to put the 2 ohm resistor in parallel with the 6 ohm resistor. So 2 in parallel with 6 is going to look like 12 over 8, 1.5. We'll go through it in steps. I'm not going to do it all in my head like a jackass. All right. So source transformation is a suggestion. So that's what we're going to go with here. All right. So I'm replacing my practical voltage source with a practical current source, which is what I have over here on the left. And then I'm going to just redraw the rest of my circuit, and then we'll talk about what exactly goes on there. You are absolutely right. Thank you. Here is VC of 0 minus. Here is I of 0 minus. All right, so what are our rules for source transformation again? Just based on Ohm's law, okay? So anytime we have a practical voltage source, we can replace it with a practical current source, where the current source's magnitude will just be the voltage source magnitude divided by the resistor. So that was a 12 volt source in series with a 2 ohm resistor. So 12 over 2 is 6 amps. And then our resistor in parallel is just the original resistor value of 2 ohms. Now we'll talk about the combinations that we can make here, okay? So 6 in parallel with 2, 6 amps in parallel with 2 amps looks like 6 amps in parallel with 2 amps. 8 amps, right. Now 6 ohms in parallel with 2 ohms is 1.5, yeah. So because I have 2 current sources in parallel and their directions are both up, I can simply add them together. So that makes this guy an 8 amp source. They're in the opposite direction, absolutely right. I understand it's been a hot minute since some of you guys took circuit one. 2 in parallel with 6 is going to be 2 times 6 over 2 plus 6. 12 over 8 is 1.5 ohms. All right. So I would argue that we are at a simplified version of the circuit to where we can determine I and B fairly, I don't want to say easily, but straightforwardly. Okay. So
Is there a reason you organize the source on the inside versus strong?
nope.
Okay.
Just
Yeah, because it's still parallel.
yep, doesn't matter either way. Exactly right. Okay, so which quantity do you guys want to tackle first? Catherine, I haven't heard anything from you today. Current. That's what I would choose as well. Okay. The reason why I would choose the current first is because once I know what this current is, I know the voltage is just 2 ohms times that current. So I might pick on you again if I don't trip over this outlet thing and break my ankle. How might we go about solving for this current? By the way, the correct answer is not mesh, just to be very clear here. I mean, it could be, but it's not. Pardon? Why don't we just do current division?
I don't know. You said no to do mesh, so I was like, I guess.
No. So current division, the reason why I suggest current division is because in parallel with our 8 amp source, we have a 6 ohm resistance. And on parallel on this side, we also have a 6 ohm resistance. What were you raising your hand about? Oh, yes. I'm sorry. Thank you. Just lousy with mistakes today. Thank you so much. So this one should be a 1.5 ohm, which is going to make our current division slightly harder to do in as much as I can't do it in my head. But at least it will be correct now, thanks to you correcting me. All right, so as I was saying, we have an 8 amp source in parallel with a 1.5 ohm resistance in parallel with a combined 6 ohm resistance. And we want the current flowing through the 6 ohm resistance. So that means that I at 0 minus is going to be 8 amps multiplied by 1 over 4 ohms plus 2 ohms divided by 1 over 1.5 ohms plus 1 over 4 ohms plus 2 ohms. Or I'm explicitly writing everything out for those of you who it's been a minute since you had to do current division. All right. So I get I at 0 minus to be 1.6 amps. Anybody has a calculator and can verify that for me, that'd be wonderful. So this is 1/6 plus 4/6. Excuse me, 1/6 over 4/6 plus 1/6. So that's going to be 1 over 5 times 8 is 1.6. Yeah, okay. Works out if we do it in our heads as well. All right. Now, VC at 0 minus is simply 2 ohms times that 1.6 amps is 0.2 volts. How do we feel about that? Seems pretty simple and straightforward. Okay. Everybody okay with our analysis that t is equal to 0 minus? We might not finish this problem today. We only have 15 minutes left of class. All right, so now we're going to analyze the circuit at t is equal to 0 plus. At t is equal to 0 plus, this is after our switch has opened up and we are no longer at DC steady state, right? So what that's going to look like is this. We have our 12-volt source. Our 2-ohm resistor. Our 6-ohm resistor. Our switch is opened up. We have our 2-amp source. A 4-ohm resistor. An inductor that's doing something. We'll figure that out in a moment. And a capacitor over here that's doing something as well. All right, so let's talk about how we're going to represent our inductor first. How did we do it in circuits 1 when we were doing a current source having the same magnitude and direction as the inductor current at t is equal to 0 minus. So that will be a 1.6 amp source, direction down. So at t is equal to 0 plus specifically, we replace our inductors with a current source having the same magnitude and direction as our inductor current at t is equal to 0 minus. And that is because the current flowing through an inductor cannot change abruptly. So here is our 1.6 amp source. What do we do with our capacitor? Voltage source, right? Because for a capacitor, the voltage drop cannot change abruptly. So we're going to replace our capacitor with a voltage source whose magnitude and polarity is the same as VC at 0 minus. .2 volts. VC at 0 minus. Here's I at 0 plus. Now, one thing that we are going to need to do here is we are going to have to figure out what our capacitor current, that is a tornado warning. Warning is the one that means there's actually a tornado, right? So watch is there's gonna be one. Warning is there is one. Might be a stopping point. Let me go see what the official protocol is real quick. Yes, it does have no exterior. All right, let's stick with it then. Tornado be damned. We got internet, so it's probably not here. All right. Okay. So we need to figure out what that quantity IC is because it's going to be required of us to calculate VC. And we also need to figure out VL, the voltage drop over our inductor. Okay. So any thoughts on how we might determine either of those quantities? Right. We obviously know what I at 0 plus is and VC at 0 plus is. Now we just need to figure out the voltage drop over the inductor and the current flowing through the capacitor.
How we do Thevenin resistance at the capacitor? Maybe a little lengthy.
So what I'm going to suggest is we determine IC first, because we can do that by simply applying Kirchhoff's current law at this node, right? We have 2 amps flowing in, we have 1.6 flowing out, we have IC flowing out. So 2 amps must be equal to 1.6 plus this unknown quantity. The unknown quantity is there, 0.4 amps. Everybody okay with that? So from KCL, IC 0 plus is 2 amps minus 1.6 amps is 0.4 amps. All right. How do we go about getting this voltage?
Apply the current resistance.
1.6 amps times 2 ohms gives us a voltage drop of 3.2 volts over this resistor, over our 2 ohm resistor. Is that the voltage drop over the inductor? No, but it is useful. So what I mean by that, if we know that this voltage is 3.2 volts. From here to here is 3.2 volts. And the voltage from here to here is 3.2 volts. What's the drop here? Effectively, we're just applying Kirchhoff's voltage law around that right-hand loop and finding that VL is equal to 0. Everybody okay with that? So we've analyzed our circuit at T is equal to 0 plus. Now we will need to analyze the circuit at T is equal to infinity because there is still a source left in the circuit, right? So at T is equal to infinity, our circuit is at DC steady state again, but our switch is open. So here's our 12-volt source. Here's our 2 ohm resistor, our 6 ohm resistor. Here's our open switch. Let's see what's going on in chat. Two amps. Four ohms. Our inductor is going to look like a short circuit. Our capacitor is going to look like an open circuit. And we need to know VC at infinity and I at infinity. Anybody care to take a crack at either of these quantities? I is 2, which means VC is 4. All right, excuse me, 4 volts. Okay, so to to summarize what we've done to this point, we have determined that our circuit is a series RLC circuit. We have calculated alpha and omega naught and determined that we have an underdamped circuit. We have analyzed the circuit at t is equal to 0 minus, analyzed the circuit at t is equal to 0 plus, and analyze the circuit at t is equal to infinity. We are now ready to use the table. So the first thing that I'm going to have us calculate is the quantity VC of t. Okay. So VC of t is equal to beta 1 cosine omega dt minus, B1 cosine omega dt plus B2 sine omega dt, all multiplied by e to the negative alpha t, plus VC at infinity. All right. So before we move forward from here, it's probably of use to us to calculate the quantity omega d. Omega d is the square root of omega naught squared minus alpha squared. So this is going to be the square root of 1/2 minus 1/4, or the square root of 1/4. Which is 1/2. All right, so from here, what I'm going to do is I'm going to say that VC at 0 plus is equal to, and then we're going to figure that out. All right, we're going to substitute in t is equal to 0 into our expression here and see what remains. All right, so what is the cosine of 0? 1. So B1 times cosine of 0 is going to give us a factor of B1. What is sine of 0? 0. So B2 times 0 means that our B2 term is going to go away. What's e to the 0? 1. So we're going to have B1 multiplied by 1 plus VC at infinity. Which means B1 is VC at 0 plus minus VC at infinity, or 3.2 volts minus 4 volts is negative 0.8 volts. If my mental math is correct. If it's not, by all means, correct. All right. Are we okay with our calculation of our coefficient B1 here? Anything seem wild or crazy? All right. The next thing that we are going to do, excuse me, is we're going to use the relationship for the capacitor current. Okay, so we're always going to use the function and then the derivative-based relationship. So IC of t is C times dV by dt. This is literally why I give you the derivative on the table. This is going to look like C times omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt e to the minus alpha 2. I C at 0 plus is just going to be whatever falls out of this, right? So obviously our cosine 0 term stays, which is going to give us C multiplied by omega d B2 minus alpha B1. Our sine omega d term is going to go away. So that gets rid of all of this. And we're multiplying this by a factor of 1 because e to the 0 is 1. All right. So IC at 0 plus is equal to C times omega d B2 minus alpha B1, where we know IC at 0 plus, we know C, we know omega d, we know alpha, and we know B1. So B2 is the only quantity that we don't know. So let's do a little bit of algebra here. IC at 0 plus over C plus alpha B1 all divided by omega d. So I'm going to put an omega d here and an omega d here is equal to B2. Now algebra check out. Plugging in our numbers where IC at 0 plus we found to be 0.4 amps divided by omega d, which was 1/2 times C, which was 1, plus alpha, which was 1/2 times B1, which was negative 0.8 divided by omega d, which was 1/2. I get B2 equal if my stylus will write. Good. But by all means, use a calculator and verify that correctly. So 0.4 over 1/2 plus negative 0.4 over 1/2 seems like it should equal 0. From this, EC of t is negative 0.8 cosine 1/2 t e to the minus 1/2 t plus 4. Literally just plugging in our values for B1, B2, and B at infinity into our response equation. All right, so we ran 3 minutes long. What I'm going to do at the beginning of class on Friday is we're going to verify all this work by simulating the circuit and showing that if we enter in this as a mathematical expression, it matches the response of our simulation exactly. We might go through and figure out what I, our inductor current I was as well, just so that we can do that. So Friday, we're going to just work a couple more example problems trying to solidify this process so that your homework isn't terrifying or challenging. All right, see you guys on Friday.
Why did we use the current going through that capacitor to find the voltage? Is that just that integral relationship?
It's a derivative-based relationship that we're in, right? So,
Okay,
yeah. So the voltage drop across the capacitor is well defined. The current through the capacitor is C times the derivative. So we're always going to use, if we were solving for the inductor current, we do the inductor current relationship first, and then the inductor voltage, because that's a the derivative-based relationship there. Okay. Technically, you can do it the other way around using the integral-based relationship, but I hate integrals because I'm bad at them. So I do everything with the derivatives because it makes it easy.